So now, let's talk about statistics and why they're making you take this. Right? Well, here's the story, right? Two guys go up in a hot air balloon, and as they're flying around enjoying the scenery, they realize they're lost. Okay? So the first guy looks at the second guy and says, you know, we're flying over a canyon, and maybe if I yell, the echoes will carry and someone will tell us where we are. So I say, okay, good. So he yells out, hello, where are we? They hear nothing back. An hour passes, 2 hours pass, 3 hours pass, and then finally someone answers, hello, you're lost. Okay. First guy looks at the second guy and says, that's a statistician. Second guy says, how do you know that's a statistician? First guy says, well, first of all, it took him a long time to get back to us. Second of all, his answer was perfectly accurate, and third of all, it was perfectly useless. So what I want you to get out of this class, okay, like my underlying deep desire here, is not that you can use any formula, you know, that we put out there. People, all of you are going to be able to use a formula. You have numbers, you plug them into formulas. People can do that. What I want you to start developing is some sense of numbers, what numbers mean. Numbers are thrown at you all the time, which is, by the way, I isolated the journalism students, okay, because I want them to pay particular attention. We're told stuff all the time, and we try to make decisions based on numbers. Now, one of the crucial factors about numbers that we never stop to think about is how do we count things? How do we count things? For example, big debates now over healthcare reform, right? Healthcare reform all over the place. Can't turn on the TV without hearing something. What's the big number that's being thrown around with respect to healthcare? Anybody know? You don't have to know the exact number, but even if you know like an approximate or what it's referring to, what is everybody talking about? You can speak up. By the way, just as a side note, people also tend to be afraid to ask questions in class. I will guarantee you that if you have a question, at least 3 other people have the same question. And if they don't, they're sitting there saying, yeah, I don't know how you get that. How do you get that? All right? So you're doing your fellow students a favor when you ask a question. But anyway, so to get back, what's the big number in healthcare reform? There's that, but even before that, why did it become an issue? Yeah, okay. The number of Americans without health insurance, anybody know a round ballpark? Yeah. No. Yeah, 45.7 is the most common number I've seen recently. You know, it's gone from like 44, I've seen 50, but like let's say in that ballpark. Okay, so let's say, and I'm taking numbers from an article I got. By the way, I bring in a lot of stuff from the Times. Sometimes their stuff is good and it's spot on. Sometimes it's really lame, but you know, and I'll point out to you when it's which. So anyway, these numbers are reasonably reliable to me because I've seen them in multiple places. So approximately 45.7 million Americans without health care. Now, okay, one question is, how did they get that number? Because when people talk about not wanting to do public health care, does anybody know what's one of the big arguments that people put out there? Like why we shouldn't pay for public health care? Anybody know? And I know it's kind of vague at the moment. I'll give you a hint, because there's a group that people don't want covered. Yeah. Yeah, okay, right? Because people say, you know, you say that so many people are uninsured. Well, mostly those are immigrants, right? Well, again, what goes into those numbers? It turns out that approximately 9.7 million are actually, they're not citizens, and approximately 6 million or more are illegal, okay? So you're starting to make sense of what that big number means, all right? If Out of 45.7, if we took off 10 million, would you still think it was important to cover the other 35.7 million? Who make up the other 35.7 million? Okay? And by the way, when I talk to you about this stuff, understand, I don't want to push any agenda. I really don't. You know, I might talk about drug companies and things like that. I don't want to push any agenda. What I want is to get you to think, to look at something and say, this seems to be reliable, this doesn't seem to be reliable. Okay? So when I talk about the numbers going into healthcare and who makes those up, I want you to understand that when somebody throws a number at you, you want to ask them, where is that number from? Who goes into that number? How did you count them? Here's a stupid, simple example. 3 sheep in a field, okay? One's a sheep ready to give birth, and one's a lamb. Are those 3 sheep? Do we count that lamb as a sheep? Well, maybe it depends on what you're doing. What about the one that's giving birth? Is that 1.5 sheep? Right? It may depend on what the purpose is. Other things in terms of counting, right? And that's sheep. That's a stupid example like sheep, right? What if you're trying to count the number of aggressive acts, right? When we talk about people, it gets way more complicated. In Britain, there was a study that reported something like 25% of young adults were guilty of assault of some kind, right? What does that mean? 25%. Who goes into those numbers? Well, you know who goes into those numbers? 25%. That seems like really large. 1 out of every 4 kids is like, you know, hauling off and hitting somebody, right? Well, they counted people who were guilty of serious assault, but they also counted as assault if you pushed your sibling. Now, I don't know how many of you out there have siblings, but we all know they deserve it sometimes, right? So again, what goes into these numbers? How do we count the unemployed? When we quote numbers, unemployment is way up there now. Where do we get those numbers from? Do we count people who have been laid off and have a part-time job? They're not making ends meet, but they're not totally going under yet because they have a part-time job. What about the people who aren't actively looking? Are they counted in the numbers or not? So one really important thing I want you to understand is how do we get our numbers? Where do we get them from? Okay? Now, that was part of the rant for today. What we're going to talk about first is an example. Okay? We're going to start off with one of my favorite examples. And we're going to use it to talk about other terms in statistics that are important. So this study is called Pygmalion in the Classroom. Now, who remembers, if anyone remembers, the Greek myth Pygmalion? Anybody remember what that's about? Yeah.
An artist who creates a sculpture that he falls in love with, and then the gods bring it to life.
Yeah, okay. Pygmalion wasn't impressed with the women around him. We will not discuss his issues. He decided he was going to create the ideal perfect woman. So he sculpts this beautiful statue. And he falls in love with the statue. And the Greek goddess Aphrodite smiles on him and brings her to life. Okay? People look at that as an example of someone living up to others' expectations or performing in accordance with others' expectations. Now, talking about a statue living up to someone's expectations is a little weird, but you get the idea. Okay? Fast forward to the George Bernard Shaw play, Pygmalion. Or, what's its famous counterpart? Yeah, the musical, right? What's that story about? Oh, come on. Some of you know it. Yeah. Yeah, okay. So what's the story? Henry Higgins gets into this gentleman's wager, and I use the term gentleman loosely, a wager over whether they can turn what they call a low-class woman, a gutter snipe, which is quite a word, into a lady, right? And they're betting on her life, essentially, that they can do this, that if they treat her like a lady, she will, in fact, perform according to their expectations and become a lady. Right? So what happens? Yeah, she really is Audrey Hepburn. They sing, you know, I could have danced all night, and every, you know, and she gets passed off as a lady. Okay. Now that speaks to, again, this idea of living up to people's expectations. Two researchers named Rosenthal and Jacobson in the mid-60s decided that they wanted to see what role, if any, this played in a regular elementary school classroom. Now, some of you have been exposed to this. We call it labeling, right? If somebody labels a kid in a class, and we know the scenario. It's the first day of first grade. All of the children are sitting nicely, right, at their desks, and little Johnny is not. Little Johnny, like, had too much sugar for breakfast, or, you know, and he doesn't want to sit still. He's never been made to sit at a desk before. He doesn't know why he has to sit at a desk, right? And little Johnny's getting antsy, and he might be acting out a little. Teacher might look over and say to herself, little Johnny is a problem child, right? And then, so she's labeled the kid in her mind. Then what happens over the year? We've seen this sometimes. Some of you, I mean, you may not have, but, or you may have seen it in some different form. What happens to little Johnny over that year? Sometimes, yeah.
She starts to treat him like a problem child, so he eventually becomes a problem child.
Yeah, right? She starts acting as if he's the problem child, and then he fulfills that prophecy, right? You guys, most of you may have gotten it the other way. You were labeled the gifted child, right? Or the smart one in the family, the pretty one, the musical one, yeah? And were treated accordingly. So Rosenthal and Jacobson said, well, what happens when kids are labeled? Can we get any empirical proof for what happens when we label children? So they did a really interesting study. They went to the teachers of a place they called the Oak School, which is a pseudonym because they don't use the real names here. And they said, hi teachers, we would like to give your children this test. This test is called the Harvard Test of Inflected Acquisition. This test, although not perfect, is a predictor of whether a child will experience an intellectual growth spurt over the next year, whether they will in fact intellectually bloom. Okay? So they gave the kids this test at the end of, a school year, and they came back in the fall and said to the teachers, all right, we have the results. The kids who score in the top 20% of this, we expect will have some kind of intellectual growth spurt this year. Okay? So they told the teachers the names of these kids who scored in the top 20%, and they told the teachers, don't discuss this with the children, and do not discuss this with the parents. Right? You probably couldn't get this past an IRB now, but it was the 60s. We were able to do all sorts of things. So at the end of that year, Rosenthal and Jacobson came back, and they gave this Harvard Test of Inflected Acquisition again. All right? What was the deception? What really happened? Well, first of all, it wasn't the Harvard Test of Inflected Acquisition. All right? It was a regular old IQ test called the TOGA, the Test of General Ability. And the kids who they said scored in the top 20%, did these kids really score in the top 20%? No, they were randomly chosen. They were just randomly chosen. What Rosenthal and Jacobson wanted to see was, if these children are labeled bloomers for a year, right, what happens to their IQ? Right? What happens to their performance over that year? So that's the setup that we're looking at. Does the labeling have an effect? So now what we're going to do is we're going to talk about different terms in statistics that will help us answer some of these questions. And we'll keep going back to this, this example to talk about that. Okay? First of all, actually, I'm not going to start with this one, the descriptive versus inferential statistics. We're going to go back to that. If I don't, tell me. Let's start with this. Okay? Rosenthal and Jacobson were not just interested in the children at the Oak School. Who were they interested in? Anybody know? Who, like, in general, who would they be interested in?
Population in general.
Yeah, all the kids who might be labeled, right? So we're going to make a distinction here between a population and a sample. A population is the entire group that you're interested in, kind of in very simple terms, okay? It's the entire group that you're interested in for a given study, you know? That can be very big. We're used to thinking of populations as very big, like the number of people who, the number of hours of TV watching that goes on in the country, right? If we're looking at the number, if we look at all the people in the country and how many hours of TV they're watching, or children playing video games or things like that, we think of those are very, very big populations to find out the number of hours anybody's playing video games in the country. Yeah? Those are big populations. But you can also have a small population, right? It depends on the study that you're doing. Let's say you're studying a very rare disease, and there are only 200 cases in the world. That's your population. Okay? I can even decide, and I'll talk about it, bless you. I'll even talk about it over the semester. I'll use you guys as a population, right? I can do that. Now, if I take a number from a population, I measure it, or I calculate a number from a population, that is called a parameter. A parameter. A number that's calculated or measured from a population. So population parameter. Parameters are noted with Greek letters. So if you see Greek letters, generally that's an indication that it's a population parameter. Now usually we can't measure our whole population. Rosenthal and Jacobson couldn't measure all children in school. So we take a subset of that population, that's called a sample. Right? It's a subset of the population. Now a sample, a number that's calculated or measured from a sample, is called a statistic. A statistic. And what we're usually trying to do is use our sample statistics to make generalizations about our population parameters. Got that? This is important. And you can stop me if you need me to repeat stuff, okay? You use your sample statistics to make generalizations about your population parameters. Right? Rosenthal and Jacobson were taking information they gained from those kids to make generalizations to all school children, whether labeling is good or bad or whatever it is, or has no effect. Okay? So this leads us back to that first page, the difference between descriptive and inferential statistics. Okay? Descriptive statistics describe, right? Descriptive, they describe the data that you have at hand. Yeah?
Oh, can you please define that?
Well, a statistic is a number or that you calculate or measure from a sample. Is that good? Okay. So descriptive statistics are statistics that describe the data that you have. Just describe the data that you have. For example, if we go back to this one for a minute, okay? These are my bloomers and these are my others, right? The kids who are not the bloomers. And those are numbers that came from the data that we had. Those are descriptive statistics. So sometimes that's all we want. But often what we want to do is we want to make inferences or generalizations to a population. So that branch is called inferential statistics. The bridge between descriptive and inferential statistics is probability. That's how we get from one to the other, is using probability. Okay? So now I'll come back to that in a minute. Yeah, go ahead. Inferential statistics, you're making inferences or generalizations to your population. Yeah?
How does that differ from descriptive?
Descriptive just describes what you have now. For example, if I have this class, right, and I find the average in this class from an exam, that's a descriptive statistic. If, however, I take that statistic and I use it in some way to make inferences to all stats students, that would be inferential statistics. And we're going to learn different techniques of inferential statistics. Okay? Okay, everybody still with me? All right. So let's talk about samples again for a minute, right? Because how we get samples is very, very, very important. The best case scenario is what we call a random sample. Anybody know what a random sample is, by the way? A random sample. A random sample means that everybody in the population has an equal chance of being selected. Everybody in the population has an equal chance of being selected. So that let's say you guys are my population, and I wanted to take a sample of 10 of you, find your grades, right? So if I put all your names in a hat, and it was shuffled really, 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 really well, because by the way, names in a hat don't shuffle very easily, right? Everybody in the class, in theory, has an equal chance of being selected, so that would be a random sample. Now, when we talk about doing studies with people, how easy do you think this is? Like Rosenthal and Jacobson, they picked a particular school, right? Is that a random sample? Well, probably they chose a school that wasn't too far away from them, right? Probably, they chose a school that gave them permission to do this, right? It's not always so easy. You guys are going to be taking part in research experiments, right? Those are samples of convenience, right? If I get information about, I don't know, some kind of cognitive behavioral task from college students, we're doing the science is fine, but my sample is not necessarily representative of the whole population. So I can what can I generalize to if I do a study just on college students? Well, it may depend. It may depend on what the study's about. But here are a couple examples of bad sampling or limited sampling. One is kind of bad, the other is more limited. So 1936, presidential election between Alf Landon and Roosevelt. There was a magazine called Literary Digest that sent out 10 million ballots to their readers, to people who had motor vehicle registration, and to people who had telephones. Okay? They got back 2.5 million ballots. So out of 10 million, they got back 2.5 million ballots. Those ballots predicted a landslide victory for Landon. We didn't have a President Landon. What happened? Anybody know? Anyone want to take a guess? Yeah.
People who felt strong to
That's interesting. It's an interesting point about this kind of stuff. It's not the answer I was looking for, but it's an interesting point, right? How many people didn't send them back? Always an issue. Yeah? Yeah? Yeah, which one? Yeah. 1936. Who owned cars? Who owned telephones? Who owned magazine subscriptions? Okay, that was 1936. People didn't have such money. So the people who responded tended to be more affluent, and they were voting for Landon. Well, Literary Digest went out of business not too long after that but the point I'm trying to make is that even though they had 2.5 million votes back, it wasn't a sample that was representative of the country. So it was useless. The Gallup people did something similar. They only sent out 50,000, or they only got back 50,000. but they predicted Roosevelt because they had a better sample. Okay? Really, really important. Sometimes you can't get a sample, a random sample, and you have to get a sample of convenience, but you should understand the limitations behind it. Another example of sampling, okay? Aspirin. Aside from headaches, what's aspirin good for? What do people always talk about aspirin should be taken for? Yeah, why? Do you know? Can you be more specific? Yeah, they say that especially for people who've had a heart attack, if you take an aspirin a day, it reduces the likelihood that you're going to have a second heart attack. Okay? Now, when this study first came out, people were blown away by the results. All right? Who were the happiest people? Who were the happiest people about these results? Yeah, there. The aspirin companies, right? Well, I don't know if they were happier than the people who weren't going to have heart attacks, but, you know. Another important thing you should look at when you look at studies is who's funding the study. Doesn't mean it's bad, doesn't mean it's wrong, but you should know. You should know. Okay? So this study, which was actually quite well done, and came up with these really good results, but who did they do the study on? The initial study? They've since followed it up with other stuff, but who was the study done on initially? Middle-aged, white, male doctors. Okay? It was totally, you could totally generalize to other white, middle-aged male doctors. But what about the rest of us? You know? Do those results apply to me? Well, how do I differ? Yeah, I'm female, but like, what's a very obvious difference between, let's say, me and the people in that study? Hint, men. They're bigger, right? I don't have the typical body mass of the average male. So if nothing else, is the dosage going to be the same? Likely not. Okay? Those are examples of how samples can really limit your generalizability. And that's an important thing to understand when you're doing this. Okay, so we have samples. Good. What's next? So now we have to talk about how we set up our research, how we understand these things. Now, an important term, you're not going to see this in the book, but it's an important term for you to know, is when we say something should be operationally defined. Operationally defined. That's when you take a concept and you know some question, but you structure it in a way that you can answer the question. Very often, I have students who have wonderful research ideas, but they don't know how to test them. Because what you have to do is you have to sit and think about, like in the Pygmalion study, right? The researchers wanted to know whether labeling affects children. So they had to think, well, what do we mean by effect? Well, let's see, maybe it would be good if we saw if it affected their IQ performance, right? So they operationally defined what was going on there. So in order to operationally define something, we have to talk about the variables of the research. And we're going to talk about variables in different ways, different characteristics of variables. So first of all, what is a variable? A variable is a characteristic or a trait in a study that varies. A characteristic or a trait in a study that varies. That is, you can get different values. Yeah, do you have a question?
Yeah, can you just redefine operational?
And just when we talk about operationally defining something, it just means that you're setting up your question in a way that you can test it. Like if I said, gee, are boys more outgoing than girls? Well, what do I mean by outgoing? You know, I have to find a way to determine what this is. Okay, so variables are a characteristic or a trait, something in the study that varies. It takes on different values. Height, weight, eye color, IQ, gender, right? They can take on different values in a study. They vary. Whereas a constant is something that doesn't change. So for example, if I gave you guys an exam, your scores on that exam are a variable. Everybody has a different score. If I then come in and say, you know what, question 13 was bad, I'm giving everybody 2 points, that's a constant, okay? Because everybody's getting the same 2 points. So when we talk about variables, we have to define some of the things we mean. Now, one thing that's important to talk about when you're doing statistics is what we call either scales of measurement or levels of measurement. Scales or levels of measurement. And these are not exactly variables. This is how we're measuring them, what we're using to talk about the variables. So for example, there are 4 levels or 4 scales of measurement. The first one is called ordinal. In an ordinal scale of measurement, the values are simply category labels. Nominal, names, they're names. So for example, if I was interested in what kind of pets people in the class owned, right? The labels would be cats, dogs, birds, fish. Okay? That's a nominal level of measurement. Oh, did I say ordinal? Oh, I'm sorry. Sorry. We can cut that for the tape. Yeah. No, nominal. I meant nominal. Thank you. Nominal. Yeah, so nominal, name. The labels are just categories. Okay? Religious affiliation, right? Christian, Muslim, Jewish, Hindu, other, right? Those are category labels. That's a nominal level of measurement. And you can't do much math with that, right? I can't add my dogs and my cats and get an average of fish. You know? So it's limited in what you can do with it. The next level up from that is ordinal. This time it's really ordinal. Okay, ordinal. Ordinal means that there is an order to the values, ascending or descending. There's an order to the values. But differences between adjacent values are not necessarily the same. Differences between adjacent values are not necessarily the same. For example, okay, a classic example of an ordinal scale is an anxiety measure on a scale of 1 to 5. Okay? You know 5 is more anxiety than 1. But is the difference between 1 and 2 the same as the difference between 3 and 4? You can't really tell that. It's a subjective measure. That's an ordinal scale of measurement. Okay? One up from that is an interval scale of measurement. An interval scale of measurement. And in an interval scale of measurement, you have your order, right? You still have order, but the intervals or the differences between adjacent values are the same. They are the same. Yeah, I'll try. In an interval scale, the differences between adjacent values or the intervals between adjacent values are the same. The classic example of an interval scale, and you'll understand why we use this example in a couple of minutes, is degrees Fahrenheit or Celsius. Okay? Because a degree is a degree is a degree is a degree anywhere along the scale, right? And we know that there's more heat if the number is higher than if it's lower. Okay? That's your interval scale. The last one is ratio. Ratio. And in a ratio scale, it has everything that the interval scale has, but in addition to that, it has an absolute or true 0 point. It has everything that the interval scale has, but in addition, it has an absolute or true 0 point. Meaning, the absence of the characteristic. A true 0 point means the absence of the characteristic. For example, height, okay? An inch is an inch is an inch is an inch anywhere along the scale. 10 inches is higher than 5 inches, right? It's more. And if you have 0 inches, you have no height. So it's a ratio level scale. So that's typical for things like height, weight, reaction time, things like that. Those are ratio level. Okay? Now why is temperature in Celsius not a ratio level? Anybody know? Yeah, the 0 is arbitrary, right? What is 0 degrees Celsius? No, I mean, like, what is it literally? You're right, yeah. But no, like, what is it? If I talk about 0 degrees Celsius, what is that? Freezing point of water, right? It's not the absence of heat. But degrees Kelvin, 0 degrees Kelvin, yeah, that's a ratio scale, because that means the absence of heat. Okay? There aren't too many scales of measurement that are interval level, as you can tell. Yeah? That's the absence of heat, but it's not 0, right? They don't call it 0. Yeah. It's when the number matches up to the thing you're talking about. It's a way to think about it. Okay? So understanding the scales of measurement, you can do higher level mathematics with things like ratio interval scales than you can with something that's nominal. So it's important to know. Another thing you need to make a distinction between is between the variable and the scale of measurement. Okay? And we'll talk about that more in a minute. But for example, if I'm looking at anxiety, right? If I'm looking at anxiety, well, let's say I just want to measure anxiety. I'm going to take all of you guys and I'm going to decide who's high anxiety and who's low anxiety. What scale of measurement is that? I break you up into two groups, high and low anxiety. What scale of measurement is that? Nominal, right? Just high or low. Or I could administer a 1 to 5 scale on your anxiety level. That's an ordinal level of measurement. What if I decided to measure heart rate as a measure of how anxious you were? Well, I would say that that's, ratio level. Okay? So just understand that, and how you measure things determines, some of the statistics you can do with stuff. Okay? What else? There was something else I wanted to say about that. I'm sure it will come to me. Okay, and so one other thing I'm going to talk about then is a distinction between continuous and discrete. And again, this is back to variables, continuous and discrete. Oh, one thing I forgot to mention, these handouts, this is the only time I'm going to give these to you. These are posted on Blackboard for the whole semester. They're posted on Blackboard. You're welcome to print them out and bring them to class. A lot of people do. And you can print them out in this handout format. Otherwise, if you print them out like that, they'll come up, in that big page that you don't want. Okay? So continuous and discrete variables. A variable is continuous if between adjacent values, there are an infinite number of values. Between adjacent values, there are an infinite number of values. This will make more sense when I give you an example. How about downhill skiing? Okay, we measure that in time, right? Completion time or whatever. Okay? So somebody finishes 5 seconds and somebody finishes in 6 seconds, right? So between 5 and 6 seconds, is there a gap there? I don't mean between the people. I mean between those two values. Well, are there other values in between there? Yeah, right? So there's no real gap. What really is, there's an infinite number of values between 5 and 6 seconds. because you can measure, 5.1, 5.12, 5.127, 5.127, right? It's only limited by your stopwatch, your measuring instrument. So really, in a continuous variable, there's an infinite number of values. Okay? Now, discrete, if your variable is discrete, that means that between two adjacent values, there's a gap. There's a gap. And usually a finite number of values. Not necessarily, but often. So what's an example of that? Well, how about students at a college, right? We don't have half a student. Or the number of children in a family. Contrary to popular belief, we do not have 2.3 children in a family. Right? It's a discrete variable. The number of children in a family, the number of books in the bookstore, it's a discrete variable. Okay? So what I want you to understand is I don't want you to confuse the variable with the scale of measurement. So if I asked you about anxiety, is anxiety a continuous or a discrete variable? You have any thoughts? Yeah. Yeah, I would say it's continuous, because there's an infinite number of shades of anxiety, as most of you know, around midterm time, right? It's a continuous variable. Whereas if I measured it, if I just looked at how I was measuring it, and I did it like on a 1 to 5 scale, then that would look as if it's discrete, but it's really not. The variable itself is continuous. Okay? Now, let's see. I'm going to go back to Pygmalion and talk about this. Oh, I know what I want to do first. So the last thing we're going to talk about here is the difference between independent and dependent variables. Independent and dependent variables. An independent variable is the variable that you're observing or manipulating, that you're really interested in. And the dependent variable is the variable that you're using to assess whether the independent variable made a difference or not. You use the dependent variable to assess, right, to evaluate whether the independent variable had an effect or not. I'll wait, yeah.
If the independent variable does have an effect, it's no longer an independent variable, right? Doesn't it become dependent?
No, I think you're mixing up your terms of independent and dependent, unless you're thinking of something else. Let me give you an example. Okay? And if this doesn't clarify it, bring it back to me, okay? I'll give you a couple of examples. First example, I talked about, is there a difference between boys and girls and in extroversion? Okay? What's my independent variable? Yeah, sex, right? And by the way, that's the variable. What are the values of the variable? No. We're still talking about the independent variable is sex. What I said was, what are the values of that variable? Boys and girls, or male and female, however you want to do it. Right? Don't confuse value with the variable. Okay? What's my dependent variable? Yeah, some kind of extroversion score. Because I'm using that extroversion score to see whether there is a difference between the boys and the girls. I'm using it to assess whether there's a difference between the boys and girls. Okay, is that better? Okay. All right, so let's go back to our Pygmalion example for a minute. Okay, our Pygmalion example. What's my independent variable? So I want to talk about a couple things here. What's my independent variable? And again, think of the variable, not the values. Yeah?
Or no, the kids that are labeled.
Yeah. Okay, exactly. The variable is, let's think of a creative name for it. Labeling group. Right? Whether they're labeled or not. something like that. And the values of that independent variable? Well, in this case, I have them labeled as bloomers or others. And by the way, it's real important to make a distinction between the variable and the values when you get to SPSS. Because when you put this in the computer, you want to know which things. Computers are great. These programs are great. You know, we can do things with these computer programs that, first of all, 30 years ago, we couldn't do at all. And we can do them in a fraction of a second. But if you put the wrong things in, it just gives you garbage, right? It'll tell you answers, but they're not right. So you have to know what you're putting in. Okay. So that's the independent variable in the Pygmalion study. What is the level of measurement? What's the level of measurement for that variable? You got 4 choices. You can do it. Yeah. Yeah, good. Nominal. Nominal, right? Because the values are only bloomers or others. That's it. They're just these labels, these names. Okay? By definition, a nominal variable is discrete, which I'm sure you can understand, right? What about the dependent variable? What's the dependent variable here? This is a little trickier. Let's see if we can get close to it, though. What's the dependent variable? Well, you're getting kind of, you have a general idea, but we need to make it more specific. Someone want to help her out? Yeah.
I was just going to say that the labeling, whether the kids that were labeled scored higher.
You're making it too muddy. You're kind of right, but all I want to know now is what the variable is, what the dependent variable is. Yeah.
How old is the numeracy?
No, again, you're getting close to it, but you have to be a little clearer. Yeah. Okay, he said IQ. Closer. Yeah.
Change in IQ?
Oh, actually, who was that? Because I was pointing back there, but that's fine. Who was it who said that? You. Oh, okay. Yeah, change in IQ. That's really what it was. Right? They gave the kids an IQ test one year, they labeled them, and then they give them an IQ test the next year. These numbers, these are change in IQ points. And by the way, this is just a kind of representative. These aren't the actual numbers. This is just representative of it. So it was actually change in IQ was the dependent variable. Is everybody clear on why that's the dependent variable? This is the important stuff to get. Whenever you're talking about any research, you have to know, what am I looking at? What am I using to assess that? And you're going to have to look through problems and say, okay, what is this variable? What is that variable? What are the levels of measurement? Okay, so the dependent variable is change in IQ. What level of measurement do we think this is? Yeah. She says interval scale. Anyone want to argue with her on that? Yeah. Ratio. Anyone want to argue with that? I have an interval and I have a ratio. Yeah. Okay, we have 2 intervals. Yeah, all the way in the back.
I would say ratio because the change can be 0.
Interesting. Anyone else want to throw in on one more thing? Yeah. Why do you say ordinal? Okay. A lot of us don't know this, right? But IQ scores, and if we're just talking about IQ, and then we'll talk about change in IQ, okay? IQ scores, the intervals between the numbers are not exactly the same. We treat it as if it's the same. We're actually treating it in this class as if the intervals are the same, but they're actually not. The difference is between 79 and 80 is not exactly the same as the difference between 120 and 121. Bless you. So even though it looks like those intervals are the same, they're not, which means it's an ordinal level variable. But so now if we go to change in IQ, so somebody said, Well, zero change means there was no change. That's true, but your intervals are still not the same. So it's still ordinal level. You got that? Anyone need clarification? All right. Now, IQ. Let's talk about IQ. If IQ is reflecting intelligence, do we think of that as a continuous or a discrete variable? Intelligence, continuous or discrete? Continuous, continuous. So I just want to note a couple of last things in this data that are just kind of important overall. We haven't learned this term yet. Probably a lot of you do know it. The mean is an average. So what those numbers are indicating is that on average, the bloomers did better than the others. So the questions that we're going to have to learn about this are, well, first of all, understand something. In statistics, we very, very often are talking about group averages. What does that mean? Does that mean that every single one of the bloomers did better than every single one of the others? No. Averages. That doesn't mean that everybody does better. So if you're talking about how well an antidepressant works, if we find out that on average it lowers people's depression scores, that's fine, but it may not work for everybody. It's an important distinction to know. Yeah?
In statistics, do you throw out like the extremes, or do you keep them in the mean?
That is a whole discussion that we will get to when we talk about the mean. Okay, you can bring it up again though. Okay, it's a good point. All right? So on average, they did better. That's one thing, that averages tell you something but not everything. Okay? There's also variability. Right? The bloomers, not everybody scored the same number. So variability is a really important concept in statistics, how spread out the scores are. It's a really, really important idea because not everybody's doing the same thing. Okay? And was there anything else I'm going to say about that? No, I think that's pretty much all I wanted to talk about with this. So we will go back at some point and we will do this. But, oh, I know, the one last question. They're different. The question is that difference between the bloomers and the others, is that due to the labeling or is it due just to chance? That's going to be a question we ask over and over again as we try to tease apart, does labeling work or does it not work? Has an effect or not? Okay?